So now let's find out what it would take to lift that thing up. Okay. So this is actually done when they're trying to bring things up from at depth underneath the water. And what they do is, some of you probably have heard of this, um, attach an underwater balloon to this thing. Okay, so we're going to tie a balloon onto there, and this thing's going to have a certain volume. Let's call it delta VA, just like that. And if you give it enough volume, then there's enough buoyant force between the balloon and that which is acting on the treasure itself to lift the whole thing up. Okay, so let's kind of see how this might work. All right, so we know we're going to have some weight here from the treasure chest, so we'll call that WC. And we know we're going to have a buoyant force acting on it. We'll call that FBC. So that's the buoyant force from on the chest. And now the balloon itself, I mean, there's going to be a rope. It's thick. I mean, it's not an ordinary balloon. So it's going to have a little bit of weight. Not much compared to the treasure, of course, but let's try to be thorough here. And so we're going to have the weight of the balloon. And then there's a buoyant force of the balloon itself. Okay, and we want those things to be in equilibrium. So if we draw it on our free body diagram, then we've got the weight of the chest. We've got the weight of the balloon itself. And then, of course, we're going to have the buoyancy acting on the chest and the buoyancy acting on the balloon. Okay, just like that. Okay, so let's see here. Let's get to this. And you can kind of see what's going to happen here is, oh, whoa, what happened there? Wow, okay. That was not what I expected. All right, so, but what's going to happen here is that the buoyant force from the chest plus the buoyant force from the balloon are going to have to equal the weight of, what did I do? Oops. We're going to have to be the weight of the chest plus the weight of the balloon. Okay, just like that. So let's start to flesh it out a little bit. And I'm going to make things just a little bit bigger here. So the buoyant force on the chest is going to be the density of water, the volume of the chest, times G. Okay, and on the balloon, we're going to have the density of the water, the volume of the balloon times G, and that's going to be the mass of the chest times G, plus the mass of the balloon times G. But the balloon is filled with air. Okay, and so we're going to have to put on here that the balloon has a density of air times the volume of air. Okay, now under the balloon, I want to make that an A so it's not quite so confusing. So we've got the density of the air times the volume of the air times G. Okay, just like that. Now, it's kind of fun here. Notice all these G's are going to go away. Boom, 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 boom. All right, just like that. So let me write that down because I don't want things to get too messy here. So we're going to have the density of the water, the volume of the chest, plus the density of the water, the volume of the balloon. So I'm calling that VA. And that's got to be the mass of the chest plus the mass of the balloon plus the density, plus the density of air times the volume of the air itself. Okay. So let's do a little bit of algebra. I want to get all my delta VAs over to the left side of the equation. And so that means I'm going to have here rho W delta VA minus rho A delta VA. And that's going to have to be MC plus MB minus rho W delta VC. Okay. So if we do a little bit more algebra on here, okay, then we can realize here that I've got a delta VA here and here. So I can pull that out, delta VA onto rho W minus rho A gets us to MC plus MB plus, oops, not a plus, minus rho W delta VC. All right, so now my volume of air is going to be, okay, MC plus M of the balloon minus rho of water delta V of the chest divided by the difference between the densities. So that's kind of an interesting result. Okay, it comes down to the difference of the densities between the what we've got in the denominator there. Okay, just like that. So if we work all that out, okay, and we're gonna have to come up with some other numbers here. So let's say that the mass of the balloon, okay, which we didn't have a number for that. We need a number for that. Let's just say it's 2 kilograms. And let's say the density of air is, let's say 1.2. What is that? I wrote it down here. 1.23 kilograms per meter cubed. Okay. Now the density of water is 1,000. So, you know, the 1.23 is not a huge, that's not really a game changer. Okay. That's not going to change that very much. So, you know, there we go. Now, if we plug all of our numbers in there, and I'm running out of room and it's already gotten pretty messy. Okay, so I'm not gonna write all that down, but what we get for our delta VA is 0.192, okay, meters cubed. Now I don't really have that doesn't mean a lot to me. I don't really know what that means. Okay, remember we talked in the last one about how a cubic meter is really pretty big. It's bigger than it seems like it ought to be. So 0.192, I don't know what that is. So what I'm going to do, so I'm going to say, well, let's suppose the balloon is a sphere, and we can take the equation for the volume of a sphere and figure out, well, what would be the radius of this balloon? Okay. And then that's going to give us a sense for this thing. Okay, so let me say that is going to be 4/3 pi r cubed. Okay, so that's the formula for the volume of a sphere. And if we solve for r when we do that, okay, what we get is that r has to be 0.358 meters. Okay, so about 36 centimeters. So the radius is about, so 10, 20, 30, you know, somewhere in here is the radius. So the diameter is going to be about like this right here. Okay. So maybe here's my balloon. It's maybe about this big right here. Okay. Size of a pretty large, maybe an exercise ball almost, you know, that size, you know what I'm talking about, with people sit on it or they lay on it or whatever. I know it was really popular a few years ago. Anyway, so that's about how big we're talking about there. Okay. Now, let's flesh this thing out just a little bit more. Okay. If we put in the density of water as what I suggested over here, 1.23, like that. Sorry, there it is. That's the density of air at STP. Okay, so at atmospheric pressure and room temperature, that's what the density of air is. So if we try to take a balloon, okay, and put normal pressure in it underneath the water, it's going to be collapsed. Okay, that's not going to work. So we're going to have extra pressure in the balloon itself. All right. And so putting extra pressure in the balloon is going to increase the density inside that thing. All right. Now, the way the pressure and the density are going to work out together, then we're going to end up having to have 3 times the volume compressed into the same space in order to get that kind of pressure. And we're going to talk about that soon. All right. So basically what I'm trying to get to is that if this thing were, say, 30 meters underwater, like we used in a previous example, then the density, by the time we put enough pressure into the balloon, the density would be about 3 times greater. Okay. How much is that going to affect our answer? Well, remember, in the denominator here, we were talking about 1,000 minus whatever we put in for row A. Okay, so whether we put in 1 for row A or 4 or 5 or 10, it's not going to be a huge difference. Okay, it's going to be a pretty small difference anyway around. Okay, so we're still looking at something like this. Okay, all right, now, second thing to explore. If we, inflated our balloon to that size, at that point, the balloon chest system is neutrally buoyant. Okay, so in other words, it's going to be just like able to just sort of sit like this in the water. Okay, perfectly neutral. We could move it around however we wanted to. Okay, and that would work just fine. But it's not going to rise to the surface on its own. Okay, in order to rise to the surface on its own, we're going to have to give it a little more volume. Okay, so if we give it a little more volume, now that buoyant force goes up, even though the weight is basically the same. Okay, but then it's going to rise. Okay, it's going to rise up just like that. Okay, now if the balloon is able to expand, if it's really a rubberized thing and not something stiff, then as it expands, then the pressure inside the balloon is going to cause the balloon to expand as it goes up. Okay, and then the buoyant force is even more. So it's going to actually go up even more quickly. Okay, so it's going to be accelerating. The closer it gets to the surface, the more this thing is going to expand. Okay, so this is a problem for people who like to deep sea fish. Fish for deep sea fish. Okay, if you reel it up too quickly, a fish has a swim bladder inside it, and that bladder could get too big, explode, and then ruin your trophy. Okay, that sort of thing. On the other hand, all right, let's say we have our balloon and our chest, and we're underneath the water, and there's like a big cliff here, and we move this thing over, let's say, and then we decide to move it down. Now what's going to happen is that there's going to be a little more pressure on the outside, and we have set the pressure to be at 30 meters. And if that thing gets moved down to 30.5 meters, then the balloon's going to get slightly compressed. All right. If it's slightly compressed, then the weight's greater than the buoyant force, and it will begin to sink, and it will never recover. Okay. And so the further down it goes, the smaller the balloon will get, and the more effect the weight has, and the less effect the buoyant force has. Okay, so these kinds of situations, they are equilibrium, but it's what we call unstable equilibrium. So if this chest was at 30 meters and we inflated the balloon to exactly a certain value here, then if we go up to 29 meters, it's going to float to the surface. If we hit 31 meters, it's going to sink. Okay. This is this is how submarines work. Okay. So in a submarine, they've got a bunch of compressed air and they've got big cavities in them. Okay. And the cavities are full of this air. All right. From the compressor. And so in order for the submarine to go up, what they do is they put a little more air in these buoyancy chambers, and then it's able to rise up like that. Okay. So if they need to rise up really, really quickly, like in a war movie or something like that, they expand those buoyancy tanks as much as possible, and then they get as much buoyancy as they can out of this thing. Okay. If they want to dive, then they release some of the air. Okay. And the buoyancy, that's like the balloon, gets smaller and they're going to go down. And once they get to the depth that they want, then they make it neutrally buoyant once again. Okay. Just like that. So by controlling the amount of air in these buoyancy tanks, they can control whether it's going to go up or down. Now, there's a maximum amount of pressure that the submarine itself, in its compressed air, has. Okay, there's a certain, let's just make something up. Let's say it's 10,000 psi. I don't know what it really is. Okay, but if the external water pressure exceeds 10,000 psi, then that means once they get down to 10,000 psi, they can't put any more extra air into those tanks. Okay, so we usually think about submarines, going down and like, oh no, I'm going to be crushed. Okay, yeah, that's danger too. But another danger that they face is that they might get into a situation where it's like the sinking balloon. Okay, if they go too low, the external pressure will begin to crush the buoyancy tanks, and then the submarine is just going to careen on down, and there isn't anything they can do about it. There's no way for them to correct and come back up. Okay. Scuba divers have a problem with this as well. With scuba divers, when you go down underwater, in order to breathe, like we talked about earlier, you're going to have extra pressure because of the pressure of the external water pushing on your chest. So if you got scuba gear, you got that tank and it's forcing, air in for you, allowing you to take a breath. All right. What that means, though, is you end up getting extra amounts of nitrogen in your blood. Okay. And some oxygen and stuff. All right. And then if you come up too quickly, your body can't get rid of that extra oxygen. All right. And so what'll happen then is just like if you've ever had a bottle of pop and you look and there's like no bubbles in there, and then you go, you turn the lid and then you got bubbles in there. That can happen in your blood. Okay. And that's not cool because those bubbles will collect in your joints. It's very painful. It's potentially lethal. And that's what's called the bends. So people that dive very deeply using scuba gear, they have to come up very slowly. All right. Which means if you're going to dive deep, you got to keep that in mind. You're like, oh, okay. I got to remember it's going to take me half an hour to come back up. Maybe it takes me 5 minutes to get down, but I'm going to have to take 5 minutes to get back up just so my body can exhale all of that extra nitrogen and stuff that's in my system now. Okay, well, how about that? We chased some good rabbits there. Anyway, that's the last video in this particular series. Okay, so we're all done with that.